Talking about Chapter 5 material, which is what we're going to start today. I want to give you a quick recap of the exam results, the exam that finished up last week. So I think this was in the notes that you had. Here's a quick look at the statistics. So the average on, I guess there's a typo, this should be spring. Anyway, the average this year was 13.1 out of 20, so that's corresponds with 66%. A little bit lower than last year's, but not alarmingly so. 0.4 out of 20 is probably in the noise in most cases. So you can see we did similarly, just slightly worse than last year. We did do better than the other sections. So there are two other sections of this course. You guys make up the majority of the students, but there's two other sections, and their average was about a half point lower than ours out of 20. So we did a little bit better than that. So that's kind of, if you want to know where you stand in regards to the average, that's kind of what we have for this. Keep in mind, no matter how you did on the first exam, it's only worth 20% of your grade, and even if you would have gotten a 0 on the first exam, you could still theoretically finish up with a B+ in the course. So that nobody's grade is written in stone or even in pencil right now. Now, the other thing I want to go over is maybe some factors that contribute to exam scores, just to give you a little bit of additional statistics. So these are not the best statistics here because we've only had 2 bonus quizzes, but one of the things the bonus quizzes allowed me to do is take attendance periodically. It would get rather tedious if I try to do that every day, but once in a while I'll take attendance, and so we can see the suggestion of a trend. So on January 29th was our first bonus quiz. The attendance was 78.5% of students here, and then on February 14th, about 2 weeks later, it dropped below 70%. So not surprisingly, this happens every semester. People attend class less and less as the semester goes on, but I encourage you to make that continuous effort. And it's not so much that coming to class is going to necessarily teach you everything you need to know, because as you all know, a lot of individual effort goes into this. But at the same time, when you come to class, that's sort of showing your regular dedication and getting you exposed to it on a very regular basis. So if we look at how the students did based on their attendance, so with 2 bonus quizzes, there are now 3 categories of students, the ones that I would call 0% attendance. Now that means they missed both bonus quizzes. It doesn't mean they never showed up to class. I don't know if they were here or not other days. But if they missed both bonus quizzes, their average was a 12 out of 20. And then if you consider the students that missed one of the 2 bonus quizzes, which means they've missed at least 1 class this semester, doesn't mean that they were here all the other times, their average was 12.1 out of 20. Now keep in mind, this is just statistics for those that attempted the quiz. It has nothing to do with whether you got it right or not. It's just the fact of whether you were here or not. And then the students that have 100% attendance means they have scores for both bonus quizzes, which means at least for those 2 days they were here, their average was 13.8 out of 20, so quite a bit higher. And then if you ever take a stats course, you'll learn about t-tests, which is determining statistical differences between different populations. If you do a t-test between these first 2 groups here, the 0% and 50% as I'm calling them, there is no statistically significant difference. So if you miss some class or you miss a lot of class, it doesn't really matter. But for the students that came to all of the classes, if we compare those 2 populations, the P result was 0.0001, which if you were doing biological research would be incredible. It indicates a very statistically significant, extremely statistically significant difference, I guess the terminology, between those 2 sets. So I think this is not a causal relationship, but it is symptomatic of the fact that if you're coming to class every day and making that effort, that shows that you're putting the day-to-day and week-to-week effort into this course that's required to succeed. And I think the exam scores on the first one reflect that. Now, obviously, within each of these populations, there's a range of scores. So there are students who probably aren't here right now that skip every class and still did fine. And then there are students, of course, that come every time and still had some trouble on the first exam. That's to be expected. So if you want your scores to improve, as I'm sure a lot of you do, you need to obviously change your habits. So I would, the standard boilerplate suggestions are come to class every week, do all 4 attempts on the homework every week. A lot of you wait until Sunday night and just do the homework assignment once. If you want to get more out of it, you should do it more than once, ideally all 4 times. And then whenever you don't understand homework questions or don't have or don't get them right, especially, you should come figure out how to do those right away and not wait until it's time to study for the exam to learn everything that you don't quite understand. So there's a lot of habits that we can develop, and I'm happy to talk to you and help you figure those things out, because as I said, it's early in the course and all of you have an opportunity to improve, but it does require you to obviously make a conscious effort to do that. All right, so that's kind of my lame attempt at a pep talk before we get into the chemistry today. So what we're going to start today, as I said, is Chapter 5. In Chapter 5, things are going to change a lot. So this is something else that I've told some of the students. You know, the first exam was 100%, or not 100%, but just about 100% conceptual type questions. It was testing your ability to understand concepts and apply them in different situations. Now we're going to get into a section of the course that is very numerical, very quantitative. So really the next 4 chapters that we're going to do are going to be, the vast majority of things you do on homework assignments and tests are going to involve calculations and numerical answers now. So it's going to be quite a bit different. So keep that in mind as we go forward, that things are going to change, which may be for the better for some of you or for the worse for others, but you just have to adjust your mindset as the types of things we'll be doing now are quite a bit different. Okay, so the first thing we're going to talk about in Chapter 5 is what's called atomic mass. So this is, as we'll see, very much related to mass number. We already learned mass number, which is the sum of protons and neutrons in a single isotope of an element, and that gives us a mass number that we can characterize that isotope by. But then we're going to talk today about atomic mass, which is a little bit different, but it's still very closely related. So the first thing we need is the unit for this. The standard atomic mass unit is, well, the unit is called the atomic mass unit, abbreviated AMU. As we'll see, as we kind of already saw, if we were to try to measure the masses of individual atoms in grams, that would be an entire, a very small number. So we use AMUs as a more convenient mass. And so what this is, what is it defined as? It's the mass of the carbon-12 isotope divided by 12. All right, so that's sort of the standard that's been used. I think very recently the International Union of Pure and Applied Chemistry, which is like the governing body for all the chemistry standards, changed the definition of AMU a little bit, but this is the one that we still use in general chemistry, and it's still largely true even with the new definition that they have now. So anyway, AMU is the atomic mass unit, and it's standardized to carbon-12. So this 12C was chosen as the standard. It's very abundant elemental isotopes. It's one that's easy to measure, which is probably the reason it was used. Also easy to purify, so you can get really good measurements on it. And so all atomic masses are going to be measured relative to this. And so this is sort of how they do it experimentally. They set the mass of carbon-12 to exactly 12.0000 AMU, and then they'll measure that isotope, and they do different experiments to measure these masses, but they'll measure that isotope relative to another element or another isotope of carbon or another element altogether, and they'll use those relative numbers to get the mass of whatever the new element is that they're trying to measure. So as an example, if we did another isotope of carbon, 1213, that you can find from experiments, it's pretty easy to do relative masses of things. It's hard to do absolute mass, especially something this small. But if you did an experiment and measured the mass of 13 carbon relative to the mass of 12, you get 1.0836 is the ratio of those two masses, which means then if we want to find the mass of 13 carbon in AMU, you would just cross multiply. The mass of 12 carbon is exactly 12, so multiply that by 1.0836, and you would get a mass of 13 carbon that's 13.0032 AMUs. Now you may be wondering, why isn't this exactly 13? And these are things that you will learn about towards the end of chemistry too. We're not going to talk about them in this class, but you have this whole Einstein E equals mc squared relationship. Whenever nuclei form, there's some amount of mass that's lost or gained in terms of the energy of that nucleus. So in most cases, you're not going to have isotopes that have even numbered AMU masses. 12 carbon is one that we set to be exactly 12 AMU, but for many other isotopes, most other isotopes, it's going to be a whole number that's usually close to the mass number. So the mass number of 13 carbon is exactly 13, and the mass of the isotope will be something close to that, but not exactly, and that's for reasons that you won't really get into in this course. Okay, so that's what we have. That's how we measure atomic masses. That's what they mean. So this gets in a little bit more about that. Why are they not exactly equal to the mass number? And as I said, this because of E equals mc squared. And so a lot of energy is released when nuclei are formed. And people that work in atomic energy use that fact to produce energy and other things. So a lot of energy is released when nuclei are formed or when they decay in some cases, as you'll learn in Chem 2. And because there's this relationship between energy and mass that Einstein came up with, if you release a lot of energy while forming a nucleus, you will then change the mass. relative to what you would expect for just adding up the masses of the individual protons and neutrons. So there's a slight difference between the mass number and then the mass of the isotope itself because of E equals mc squared. Now, another thing to keep in mind is that when we look at the periodic table of elements, the mass numbers for all the elements are given, and those are also not going to typically be whole numbers. In many cases, those are very far off from whole numbers because the atomic mass that we report on the periodic table is the average of all of the isotopes for that element. So if we let's go to the periodic table and look at some of these, so you can see what I'm talking about. If we go to the periodic table, we haven't talked now about these other numbers. So we have the atomic numbers above the element, but on your periodic table you have these numbers below that represent the masses. These are what are called the atomic masses. And you'll notice that almost none of these are whole numbers. Oxygen's pretty close to 16. Some of the newer isotopes aren't measured as precisely, but there's really nothing that's exactly a whole number. And that's not just because of E equals mc squared. That's because these numbers on the periodic table are averages of all of the isotopes for that element. So we'll see some examples, but if you look at some of these, like chlorine is one we'll see, it's 35.45. It's nowhere near 35 or 36 actually. So you have a lot of atomic masses that are in between whole numbers, and that's because these numbers represent averages of all the isotopes that are naturally present for that element. And so to define that, then you need what's called the percent abundance, which is the relative amount of each isotope that you have in a natural sample of that element. So that means if you go out somewhere and you mine an element from its natural sources, it's going to have a ratio of isotopes present. That's going to be true across all different samples of that from around the world. If you went to different parts of the universe, I suppose it's possible that those ratios would change. But here on Earth, which is where we do most of our chemistry, the relative amounts of each isotopes is a fixed amount, and then we use that to calculate what that atomic mass is. So as an example, for carbon, which we've been talking about, if you go to the periodic table, you'll see that the atomic mass of carbon is 12.01. It's just above 12. So I told you that the atomic mass of the carbon-12 isotope was exactly 12. So the fact that this atomic mass of naturally occurring carbon is not exactly 12 tells you that there has to be at least one other isotope that contributes. If carbon-12 was the only isotope of carbon, this number would be exactly 12, but it's 12.011, meaning that we have some contribution from other isotopes. And so what we have in carbon is, as you might guess, because the mass is close to 12, carbon-12 is the majority, 98.89%. But then you also have a significant contribution from 13C. And then you've probably heard of carbon-14 dating. There's a very small portion of carbon which is also radioactive, carbon-14. But to two significant figures, 100% of carbon is either the 12 or 13 isotope. So that's why the mass of carbon is not exactly 12 on the periodic table. It's because you have a small contribution from 13 carbon. 1.11% of all carbon atoms in the universe have 7 neutrons instead of 6, have a mass number of 13 instead of 12. All right, and then when we report atomic masses on the periodic table, the atomic mass that we see is the weighted average of all of those. So it's the weighted average of all isotope masses. Now isotopes are often given as percentages. For the weighted average, we just use the fractions, which would be the percentage divided by 100. So if we have a bunch of different isotopes, we'll just call them A and B and so on. The atomic mass is going to be the fraction of isotope A times its mass. So we need to know the individual isotope masses as well, which, as I said, are not exactly equal to the mass number. And then you're going to add that to the fraction of whatever other isotope you have times its mass. And it is sometimes possible to have more than 2 isotopes, and in a lot of cases that's possible. So you just keep doing this for however many isotopes you have. So these fractions, again, are the percentages divided by 100. The sum of all the fractions should equal 1, or the sum of all the percentages for however many isotopes you have would equal 100. And once you know all those fractions and all the individual masses, you can calculate then the atomic mass that you would find on the periodic table. All right, so let's do an example of this to see how it works. We have boron. The element boron consists of two isotopes, just like carbon does. Boron 10, which is 10.01294 AMU, and then has an abundance of 19.9%, 19.90. And then the other isotope is boron 11, 11.00931 AMU, and an abundance of 80.10%. So we want to determine the atomic mass of boron. So as we just said, the way we do this is we take the weighted average of all the isotopes. So we're going to take the fraction of one isotope. The first isotope that we're given is boron 10, doesn't matter what order you put them in, obviously, times its mass. Then we're going to add to that the fraction of the second isotope that we have. Times its mass. There's only two isotopes in boron, as we're saying here, and we notice that the percentages do add up to be 100, so we're not missing anything here. So we just have to use these two terms. If there's more than two isotopes, you'd have additional terms to add on. Now we need to get the fractions first. So we're given percents, and as I said, fractions are just percents divided by 100. So the fraction for the boron 10 isotope is just going to be its percentage, 19.90. divided by 100. So don't mess up this. If you forget to convert percentages into fractions, you'll get answers that are 100 times too big, which will hopefully strike you as odd. But you have to make sure you remember that. For 11 boron, we take this percentage, 80.10, and divide by 100, so it's 0.8010. Okay? So those are the fractions that we get. We have to use those numbers when we're calculating weighted averages, not the percentages. Percentages are out of 100. And so finally we plug all the numbers in. The atomic mass is the first fraction, 0.1990, times the first mass. The mass of the boron 10 is 10.01294 AMU. The fraction of the second isotope is 0.8010, and then multiplied by that mass, which is given as 11.00931 AMU. And so when we plug those into our calculator, we get 1.993 plus 8.818, and that comes out to 10.811 AMUs. Alright, so that's the atomic mass of boron, 10.811. If you want to verify that you did this correctly, or at least that I gave you proper numbers, we can go to the periodic table and see that boron has a mass of 10.811. Okay? So it matches up. So that's how you would calculate that number if we gave you all the information. So this is one type of problem you could do. We give you the fractions, we give you the isotope masses, and you go ahead and calculate the atomic mass from that. Now the other way we could do this, of course, is leave out one of these other terms as the unknown. So we have this relatively simple equation that relates atomic mass to the fractions in the isotope masses. We could have left one of those as the unknown and had you find whatever that was. So if we go to this problem here, this is an example of that. We have chlorine, which is a yellow gas as I'm showing. It has an atomic mass of 35.45. It has two naturally occurring isotopes, which we're giving you the masses of. 35 chlorine and 37 chlorine are the two isotopes that you find. And what is the percent abundance of 35Cl? Now, as you might suspect, we look at this problem and we think that we actually have two unknowns because we don't know the fraction of either isotope right now. All right, so whenever you have two unknowns, you need two equations. That's algebra. That's the way that works. So I'm going to define those. We have two fractional abundances that we're trying to find, and then we're going to convert that to a percent. So we have 35Cl has some abundance. We'll call that X, so I don't have to write it out a million times. And then we have fractional, I guess is a better way to say that. Fractional abundance of 37Cl we'll call Y. So we have two unknowns, so we need to set up two equations that relate them. So we can do this in either order, but remember one of the equations we have relates the atomic mass, which we're given, to these abundances and the individual isotope masses. So the atomic mass of 35.45 is equal to the mass of the first isotope, 96885, times its isotopic abundance, which we're calling X, that's the abundance of 35 chlorine. So when you're doing these types of problems, setting up the two equations is part of the challenge. Make sure you keep your variables straight, and what does X represent, what does Y represent. So if we're calling X the fractional abundance of 35 Cl, we'll multiply that by the mass of 35 Cl, and then we'll add to that the mass of the second isotope, 36.96590 times Y. So this equation here, this first one we set up, is exactly what we did in the last problem where we were given the abundances. So the atomic mass equals the mass of each isotope times its abundance all added together. So that's what we get for this first equation, but that's not enough because you can't solve a single equation that has two unknowns. And so the second equation, which many of us always forget about, is if you have two fractional abundances, X and Y, what do they have to add up to be? 1. So that's our second equation. And then when we want to solve, what we're solving for here is the abundance of 35 Cl. We're solving for X. So the most streamlined way to do this is to rearrange this equation in terms of X. So Y is equal to 1 minus X. We take this and we substitute it into here. So I'm not going to go through all the algebra, but what we end up with is an equation that now looks like this. 35.45 is equal to that first mass times X plus the second mass, which is the other isotope. One of these days I'll write them correctly. 96590, and then we substitute in 1 minus X for that. So we replace this Y with 1 minus X, which is the relationship between those two abundances. And then following another round of algebra that I'll skip, so now we're just down to one variable, so we can all do that. We get X is equal to 0.7590, which means the percentage is going to be 100 times that. So this is one of those parts in the course. We saw this for mass percent and mass fraction that we did earlier. You have to keep straight what we're asking for. Are we asking for a percentage or a fraction? Here we're looking for the percent abundance, so we're going to multiply our fractional abundance times 100 to get 75.90%. Alright, so that's the abundance we get for 35 Cl, and that matches with choice C. The other abundance, if we wanted to calculate that, would be choice A, 24.10. It's 100 minus that. Okay, so any questions on that concept and how to do those types of problems? Okay, so that's sort of the first type of problem you'll see in this section. I mentioned there's a lot of numerical things going on here. Now the next thing we're going to talk about, which is going to be a very important concept for the next two chapters, is the mole. Well, we're not talking about animals, but that is a picture of a mole, the animal. But what we're talking about here is a counting word that we're going to use in chemistry to represent a collection of atoms or molecules or particles or whatever it is we're talking about. So a mole is just a counting word. So we've all heard of a dozen. A dozen is 12 things. A gross is maybe not as common, but that's 12 dozen, or 144 things. So if I was to bring donuts for the entire class, I would need a few gross, although I'm not promising to do that, so don't hold me to that. But anyway, that's what a gross is. And then a score, if you remember Abraham Lincoln's one of his famous speeches, 87 years ago, that meant 87 years ago because the score is 20. So all of these are counting words that we use in our everyday language, and the mole is just a counting word that we use in chemistry to represent how many things we have in that mole. So, a dozen we can say can apply to any different object you want, and same with a mole. A mole can apply to any different object you want, although practically speaking we apply it for very small things like atoms and molecules and electrons and things like that. So how many things are in a mole? The number is all familiar to you if you've taken high school chemistry, 6.022 times 10 to the 23rd. So that's how many things we have in one mole. Now this is Avogadro's number is what it's called. Now what I want to emphasize about Avogadro's number is that Avogadro didn't come up with it. He was very famous for other things. We learned about his observation that he made about chemical reactions of gases early on in this course, and we'll talk about Avogadro's law in more detail in another section. So that's really what he's famous for. The person that came up with Avogadro's number, they just sort of, I guess they had a man crush on Avogadro and wanted to name it after him, but He didn't actually come up with it himself, as far as I know. So Avogadro's number was what we call that, and that's how many things there are in 1 mole of anything. Now, you might look at that and think that it's a very big number, which it is. So before we go into how we use this in chemistry, I want to give you an idea of how big it actually is. So let's say we were going to cover the entire United States of America with 1 mole of M&Ms. So what we're going to do essentially here is we're going to cover the entire United States, and we're going to keep stacking those with additional layers of M&Ms until we use our full 1 mole. Now imagine how long it would take you to cover the floor of your dorm room with M&Ms and then extrapolate that to the entire United States. You can already imagine this is a big project. So if we were to do this, if we were to take 1 mole of M&Ms, we can do sort of some back-of-the-envelope calculations. I'm not going to run you through these, but if we assume that the volume of 1 M&M is 1 cubic centimeter, it's probably a little bit bigger, or sorry, a little bit smaller than that, but we'll just make that assumption. And then if we know that the area of the United States is 3.02 times 10 to the 6th square miles, which we'd have to convert into square centimeters, what we would calculate from this information, as I said, I'm not going to go through the calculation, we would have to stack how many layers of M&Ms do you think we would need? So, like I said, we're going to cover the entire United States with M&Ms, and we're going to keep covering them with additional layers until we use 1 mole of M&Ms. Any guess for how high our stack of M&Ms would be? Would it be a few M&Ms high? Would it be many? Or what do you think the order of magnitude would be? And just anybody have a random guess? We're just 5. A mile. So someone said 1 mile. That's actually not too far off. It's 50 miles, actually. So you're on the right order of magnitude, or close. So we would have to stack M&Ms 50 miles high over the entire United States to use up 1 mole. So hopefully that gives you an idea of how big the mole is. Or that corresponds to 8 million layers. Alright, so just an absurdly large number for everyday objects. And we would, in all reality, we would run out of time long before we finished stacking these M&Ms. We'd all, go on to the next life or whatever happens to us after we die. So the reality is this is a huge number. Or another way to think about moles is how many teaspoons of water are there in all of the world's oceans. So we know, teaspoon is just a regular spoon that you would use to cook or eat soup with or something like that. So the volume of the oceans are around 1.3 times 10 to the 9th cubic kilometers. And if we were to convert this volume into teaspoons, so how many teaspoons of water are in that volume of ocean, it comes out to really close to Avogadro's number. So you have about a mole of teaspoons of water in the world's oceans. So in other words, there are the way that people like to think about this is there are more molecules of water in a teaspoon than there are teaspoons of water in the entire world. So that gives you an idea of how big this number is, and again how small atoms and molecules are, which is what we're going to be using when we count this number. So that's just some fun little facts about Avogadro's number and giving an idea for how big it is. The most important thing for us is to know how to use it in a chemistry context, obviously. Alright, so let's first talk about the relationship between atomic mass and moles. Alright, so we now know that one definition of Avogadro's number of a mole is 6.02 times 10 to the 23rd objects in a mole, which we can use as a conversion factor, as we'll see in a little bit. But then another thing that's important is the relationship between mass and moles. So this atomic mass that we talked about earlier, which is often for a single atom thought of in terms of AMU, but the atomic mass also represents the mass in grams of 1 mole of an element. And this is an exceptionally important relationship for us that we'll use all the time. So the mass of 1 mole of an element is equal to its atomic mass. So we saw that the atomic mass of carbon was 12.011. And that means if we have 1 mole of carbon atoms, the mass will be 12.011 grams. Alright, so that's a pretty important and pretty fascinating relationship between atomic mass and moles. And so now with this in mind, we now have two unit conversion factors that involve the mole. We know that there are 6.022 times 10 to the 23rd atoms or molecules or whatever things we're interested in per mole. And because these are unit conversion factors, we can write it in either way. We could put 1 mole on top and Avogadro's number on the bottom, or vice versa, depending on how we're using it. And then finally we have the atomic mass of an element in grams is equal to 1 mole as well. So we have another conversion factor involving grams and moles. And so what we're going to do for most of today is look at different ways of using these relationships before moving on to some slightly more complicated things. So we have these two relationships for the mole, and we want to learn how to use these conversion factors in a number of different settings. So the first thing we're going to do is just do some relatively simple problems where we're using these. Alright, so let's say we have a cylinder of helium. If you're organizing a birthday party and you need a cylinder of helium, it's a standard size, one that's about the same height as you or so. It has 239 moles of helium. We want to know how many helium atoms are in the cylinder. Alright, so when we're given problems like this, we have to start now learning how to use conversion factors effectively. This is the way that I like to do these problems, and this is the way that you're going to want to learn how yourself. So if we want to know how many helium atoms, the way I like to set these up is write down what we're looking for. So we're looking for the number of helium atoms, and then write down what your given information is. So you go to the problem and find out that we're told we have 239 moles of helium. The abbreviation for moles is MOL, a very unsatisfying abbreviation, but that's what we use. So that means moles of helium, 239, and then we have to think about what conversion factor we use. So right now we have two conversion factors involving the mole. One involves mass, one involves number of atoms. We're looking for number of atoms. We don't have any information about mass, so that's what we're going to use Avogadro's number. So if we want to find out the number of entities in a mole, we use Avogadro's number. Now we have to know if this goes in the numerator or the denominator of this unit conversion factor. So we want moles to cancel out, so we put that in the bottom so that it cancels out with this mole. And then we're looking for the number of helium atoms. That's going to go on top. And so remember, Avogadro's number is that many atoms per mole. So we're going to put 6.022 times 10 to the 23rd helium atoms for every 1 mole. We want to use the conversion factor in that way. And so that means, that means that this is going to cancel out. Moles of helium cancels out. We're left with the unit we want, which is number of helium atoms, and so we stop there. So when you're doing unit conversion problems or anything that involves a lot of conversion factors, I think it's helpful to consider what you're looking for, and then once you get there, once your units match, you stop and you don't do any more calculations. So this is a simple one-step calculation, and so what we get is 1.44 times 10 to the 26th helium atoms in 239 moles of helium. Okay, so the take-home message from this example problem is if we're counting individual atoms or molecules, which in a practical sense is not something we often do, but in this class we will, because we want to know that, understand that relationship. But if we're counting individual atoms and molecules, we just need to use Avogadro's number. We don't have to worry about anything else. And what you'll notice in this problem is that we didn't need to know that this was helium. The fact that this was helium and not some other gas never came into play when we're calculating it. So if you're using Avogadro's number to calculate the number of atoms or molecules, we don't need the identity of the substance, because that relationship will hold for any substance. So in this case, and in any case like this, it doesn't matter that it is helium. We just use Avogadro's number as our conversion factor. So if we had a cylinder of nitrogen instead, but it had the same number of moles, 239, the calculation would look identical. If we had a cylinder of oxygen, same thing. So when you're converting moles into number of particles, it doesn't matter what the identity of those things are. You just use Avogadro's number. That's the relationship that matters. Now in another type of problem, let's do one that involves mass now. So let's say we have an American Gold Eagle bullion coin. I guess kids these days are collecting virtual coins and not real coins, but if we wanted to reinstate the gold standard and start collecting gold coins again, we would have a standard gold coin has a mass of 31.1 grams and it's pure gold. So we want to know how many moles of gold are in this coin. All right, so in this case, we're giving you the mass of substance, and if we give you the mass, you need to know what the substance is, because the relationship between mass and moles is going to be the atomic mass, which depends on what the substance is. So again, write down though what we're looking for before we get into those, start thinking about it too hard. We're looking for the number of moles of gold. Gold is a symbol AU. We write down what our given information is, which is 31.1 grams of gold. God, that desk at the front of the room is like creeping me out. I keep thinking someone's like sneaking up on me. Anyway, it's just a desk, so I can calm down. All right, so we have 31.1 grams of gold. That's what we're given. We want to go into moles. So we have to think if we have a conversion factor that goes between grams and moles, which we do. So we want the grams to cancel out. We want to end up in moles, and we do know now that the relationship between grams and moles is directly given by the atomic mass. We have one conversion factor that will do this for us, but because we have mass instead of just number of moles in this case, we have to know the identity of the substance, which we know is gold. And so we have to go to the periodic table to find what the atomic mass is. So if we locate gold in the periodic table, it's number 79 here, and this number, 196.97, is the atomic mass. That means there's 196.97 grams of gold in 1 mole. So that's the conversion factor we're going to use. So with substances, you do need to figure out what the mass is. We're often not going to give that to you, the molar mass, I should say, the atomic mass. And so 1 mole of gold has a mass of 196.97 grams. And so the 196.97 goes in the denominator because we want grams to cancel out, and we want to end up in moles. So it's 196.97 grams per mole. We can write that ratio in either direction depending on what conversion we're doing. And so this, again, is just a simple one-step problem that gives us 0.158 moles of gold. Okay? So the take-home message here is, if we're converting mass into moles, or vice versa, you do need to know the identity of the substance because it's determined by the atomic mass. All right, so here we had to know it was gold because the fact that it was gold dictated that we put this number in the denominator of that conversion factor. If it was a different substance, we would have had to put a different number down there besides 196.97. Okay, so any questions on these one-step problems? Yeah, sorry? Yeah, we're getting to stoichiometry soon, so we're kind of introducing a lot of the basic tools and approaches we'll use, and we're going to apply a lot of these things when we do stoichiometry, which is chemical reactions, but we're not quite there yet. So these will be important steps that are involved in those types of calculations as well, but for now we're just looking at the basics of that. And so if we go on, anything else on this one before I skip forward? Okay. So we go on to this one, a slightly more complex example. So let's say we have, this is from a few years ago now, a nanoparticle was found to have a 1.3 nanometer diameter, and it was determined to have 37 indium atoms in the structure. So there's a lot of other things in there, but we know that there's 37 indium atoms. We want to know what is the mass of indium in grams in one of these particles. So in other words, what we're asking here is, what is the mass of 37 atoms of indium? The fact that the diameter is 1.3 nanometers is not important in this case, as we'll see. So it's important a lot of times when you're doing problems like this, word problems, involving conversions and other types of calculations, sift through the information and try to figure out what's important. And nowhere in any of this have we found, or do we have a relationship that involves the size of a particle related to its moles, or its mass, or anything like that. So we're going to ignore that one, as we'll see, and there's really nowhere for us to use that. So try to figure out which information is important. And what's important here is we have 37 indium atoms, and we want to know what's the mass of those in grams. So we're looking for the grams of indium in one of these particles. So we know this particle, and we start with our given information, 37 atoms. Now, do we have an easy conversion factor that goes from atoms to grams? Anybody think of one? It would be possible to find one, but remember the conversion factors we have involve either number of atoms or particles to moles or moles to grams. We don't have a direct one to go from the number of atoms that we have directly to grams. So this is going to be a two-step problem. So we have the number of atoms, so the first thing we're going to do is convert that into moles, because we do have a relationship that involves moles and mass. So we have to sort of think ahead a little bit. So we want to convert into moles of indium first. And we know that we have this many atoms, so if we want to convert between atoms and moles, we use Avogadro's number. This time Avogadro's number goes in the denominator. So we have 6.022 times 10 to the 23rd atoms of indium in 1 mole. So the atoms cancel out. That gets us into moles. But we look at here is we're trying to go all the way to grams. And so we need the molar, the atomic mass of indium, which is going to relate the grams of indium to moles. So we have to go back to the periodic table to find its atomic mass. So indium is over here, number 49. The atomic mass is 114.82. So that's going to be the relationship between grams and moles once we have that first step. Okay? So we want moles of indium to cancel. That's an intermediate unit for us. And so in every 1 mole we have 114.82 grams. So then grams cancel out. Oh, no, sorry, grams don't cancel. That's what we want. Sorry. And that leaves us with then the unit we want, which is grams. And so we get 7.05 times 10 to the minus 21 grams. All right, so again, a very small number because we only have 37 individual atoms, which is a very tiny amount of atoms on the scale of our life. So this is how we would do a two-step calculation. We don't have an easy way to get directly from number of atoms to amount in grams, but if we do a two-step calculation, we convert to moles first, and then we do a second step. So as long as the conversion factors that you're using are valid, you can do as many of these steps as you need to get from where you're starting to where you're going to. Okay? All right, so that's one example of a two-step problem, and then we can do one more here. So now we've really made bank, and we have a solid gold bar instead of just a single coin. And so in this case, the mass is 12.4 kilograms, which is about 25 pounds. So they're quite heavy, these gold bricks. I don't think I've ever held one in my life, though I certainly would like to. So anyway, how many gold atoms are present in a gold bar? All right, so again, we're given the mass in kilograms, and we want to know how many atoms there are. Just like the last problem, we don't have really a direct relationship between the number of kilograms and the number of atoms, so we have to think about how to do this in multiple steps. So again, start with what you're looking for, which is the number of gold atoms. And then you write down what you're given, which is 12.4 kilograms. Now, one thing we should recognize in these problems is that the relationships that we have involving mass and moles are always in grams. Remember, atomic mass is grams per mole. So if our mass is in kilograms, the first thing we should do is convert it to grams if we want to relate it to moles. So here we're looking for how many gold atoms. So if you're looking for the number of atoms, you should automatically think of Avogadro's number, moles, and so we need to get to moles first. All right, so we're going to convert from kilograms into grams. Okay, so we have to remember our prefixes. Kilo is 10 to the third, so there's 1,000 grams for every 1 kilogram. So kilograms cancel, that gets us into grams. The next step is we want to convert into moles. So now we're really, where we are now is pretty much backwards from what we did in the last problem. We want to convert from grams into number of atoms. So we don't have a direct relationship, but if we convert grams to moles first, then we can use Avogadro's number. So the atomic mass of gold, as we saw in a previous problem, is 196.97. We want grams to cancel out. We want to go into moles. So we're going to put the 196.97 in the denominator, this grams per mole, and then the 1 mole up top. So that cancels out grams. Now we're in moles. Again, many students, when they do these problems, they stop here. But remember, moles does not tell you how many individual atoms there are. So if we want to know the individual atoms, we have to then use Avogadro's number. One last step, 6.022 times 10 to the 23rd gold atoms for every 1 mole of gold. And we need to write it this way so that moles cancel out and we're left with how many gold atoms we have in total. Okay, so when we're using these conversion factors, I can't stress enough to always write down the units. It's a relatively regular occurrence in this section of the course for a student to come ask me for help on a problem, and they show me their work without writing down a single unit, and I try my best to hold back my frustration, which I'm usually pretty good at. And then I find out that the reason they didn't get the answer right is because they used one of their conversion factors wrong because they weren't writing out the units. So writing out the units is going to be a lifesaver in this part of the course. So you might think you're saving some time by not writing them out, but in many cases you're going to introduce the possibility of mistakes. And here we're doing a 3-step conversion. We go from kilograms to grams, grams to moles, moles to number of atoms. We'll see in some other problems we do a little bit later that we could have even more steps than 3. So writing out your units is going to be crucial for this, so that you keep track of all the individual steps and know whether, for example, does the Avogadro's number go in the numerator, the denominator, and so on. So writing out the units is helpful. And so if we do that, we've canceled out all the units we don't want. We're in a unit that we do want, which is number of gold atoms. And the number is, again, a quite large one. Okay, so as I already said earlier, using Avogadro's number to calculate the number of individual atoms is not the most useful thing. There's no way for us to go into the lab and easily verify that there's this many atoms in 1 mole of gold, because as I said, counting that high takes forever. But we want to know in this course at least the relationship and the definition of Avogadro's number and how to use it in these types of problems. So you will see a fair number like this on the test. Okay? So any questions on the definition of a mole and how to use atomic mass and those types of things? All right, so what we're going to move on to now is closely related to that. So we said that the atomic mass is the number of the mass of an element in 1 mole in grams. And now we have a related concept called molar mass, which is more general. And I actually slipped it up and used the term molar mass a couple times already today, if you notice. So molar mass is a more general term, which basically just means the mass of 1 mole of a compound. And I guess you could just say substance in general, because this will also apply to elements, not just compounds. Units are still grams per mole. So for a simple monatomic element like gold, the molar mass is the atomic mass. Remember, the atomic mass is the grams in 1 mole for an element, so in that case the molar mass is the atomic mass. But for a compound, we have to describe and define what molar mass is for something that has a combination of different elements in it. So there are a bunch of synonyms for molar mass. You'll sometimes see this referred to as molecular weight, especially if you're talking about a compound, which is what we're going to be dealing with in this part mostly. Or sometimes formula mass or weight. We usually use mass and weight interchangeably in chemistry. So if you don't accuse me of not knowing physics, it's just that we don't use it that way in chemistry. So we use mass and weight interchangeably. And then there's some abbreviations for this that you'll see. One that you might see on the homework assignments, because at least our old book used, I don't think our current book does, is like this big fancy script M. Or sometimes you'll just see MW for molecular weight. So there's a few different abbreviations for what all refer to the same thing. It's the grams of substance in 1 mole. And now we're going to talk about how we do that for more complicated things than just single elements. So if we have a compound and we want to know what its molar mass is, the way we calculate it is relatively straightforward. We just add together the individual atomic masses. So we can get atomic masses from the periodic table. If we know the chemical formula of our compound, we take those individual atomic masses and we add them together to get the molar mass or the molecular weight of our compound. Alright, so if you have a compound, you do need to know the chemical formula to be able to determine the molar mass. But once you have the chemical formula, you just add up all of the individual atomic masses in that formula, keeping in mind that the subscripts in the formula will tell you how many of each of those you have. You'll have to account for that. So this is best going to be learned with examples, so we'll get to those here right now. Alright, so let's say we have glycine, which is the simplest amino acid. The chemical formula for glycine is C2H5NO2. And we want to know the molar mass of glycine, which would be the mass in grams for 1 mole of glycine. And as I said, the way we do this is we just use the chemical formula and we add up all of the individual atomic masses. So what the chemical formula tells us, we've talked about chemical formulas in the context of individual atoms and molecules. So if we read this formula as C2H5NO2, the way that we dealt with this in chapter 3 and 4 would tell us that, well, that means that 1 molecule of C2H5NO2 has 2 carbon atoms, 5 hydrogen atoms, 1 nitrogen atom, and 2 oxygen atoms. That's of course true, but these subscripts in chemical formulas can also be interpreted in terms of moles. So that means if we have 1 mole of C2H5NO2, this is going to contain 2 moles of carbon, subscript of 2 on carbon, 5 moles of hydrogen from the subscript of 2 that we have on H, 1 mole of nitrogen, and 2 moles of oxygen. So we can interpret chemical formulas now both in terms of moles or in terms of individual atoms and molecules, however is appropriate or convenient for that type of problem. So if we're calculating the molar mass of glycine, we recognize now that each mole of glycine has 2 moles of carbon, 5 moles of hydrogen, 1 mole of nitrogen, 2 moles of oxygen. We add up the masses of all of these individually, and that will give us then the mass of 1 mole of glycine. So for the molar mass of glycine, we know that we have 2 moles of carbon, so we're going to take the atomic mass of carbon and multiply it by 2. We have to get these individual masses from the periodic table. Alright, so carbon, as we said, is 12.01. We've already seen that one before. That's the atomic mass of carbon. So we have 2 carbons, each with a mass of 12.01 grams per mole. So that's our carbon contribution to the molar mass. We have 5 hydrogens. Wish I could switch back and forth faster here. So hydrogen is the first element, 1.008. That's the atomic mass of hydrogen. So that's going to go into our calculation, but we have to multiply it by 5 because there's 5 hydrogens. So that's hydrogen, and then we have to add up nitrogen and oxygen. So we only have 1 nitrogen. The atomic mass of nitrogen from the periodic table, I won't go find it again for you, but it's 14.01 grams per mole. So that's our contribution from nitrogen. And we have 2 oxygens, so we have to take 2 times the atomic mass of oxygen, which is 16, or 15.999 or something like that. That's close enough to 16 if we just care about 2 decimal places. So we add up all the contributions from the elements, accounting for how many of each of them there are in the formula, and that gives us 75.07 grams per mole. Okay, so 1 mole of glycine would have a mass of 75.07 grams. Okay, any questions on that one? Alright, the next one is the same thing, but we just want to make sure this one's a little bit more complicated of a formula. So let's say we have lead-4 sulfate. So here we didn't give you the formula, so you have to determine it yourself. So this is stuff we learned back in chapter 3 about nomenclature, so we have to be able to convert between the name and the formula still. So lead-4 sulfate tells us that we have, and I should tell you that this lead is Pb. That's not one you'd be expected to know, but it's a pretty common one. But anyway, lead-4 tells us that the lead has a charge of +4. And then we have sulfate, which we have to remember is SO4 2-. So this is an ionic compound, metal with a polyatomic anion in this case. And so if we want to find the correct formula for this, we need to balance the charges. And so when we balance these, we get lead, and then we need to have 2 SO4s, 2-, to balance the charge. Or alternatively, like, you can take the subscripts, the charges and make them subscripts. You would get Pb2 SO4 4, then we have to take the lowest ratio, which is 1:2. Okay, so you need 2 SO4 2- to balance the charge. So this is the formula then we're going to use to calculate the molar mass, or the formula mass as I'm calling it here, same thing. Although formula mass is more commonly used for ionic compounds. Okay, so if we want the formula mass for this, our formula clearly just has 1 Pb, 1 lead, and the atomic mass for Pb is here, 207.20. That's the atomic mass for lead. So we have one lead with a mass of 207.20. And one of the reasons I gave you this problem was to make sure we understand how these parentheses work. So if you have SO4, but then the whole thing has a 2 after it, that means we have a total of 2 sulfurs, right? We have 2 SO4, 2 minuses, so we have each one has 1 sulfur, but a total of 2. So there's going to be 2 sulfurs. So this is our contribution from lead. For sulfur, we have an atomic mass of 32.07. I won't look that one up, but that's what you get on the periodic table. And then finally, our contribution from oxygen. Each sulfate has 4 oxygens, but then there's 2 sulfates in the formula, so you have a total of 8 oxygens. So just make sure, especially for ionic compounds, when you have parentheses involved, count the individual elements correctly. So you basically multiply what's inside by what's outside. There's 4 oxygens per sulfate, 2 sulfates total. That means you have 8 oxygen atoms in your formula. So the atomic mass contribution from oxygen has to be multiplied by 8. We saw in the last one that the atomic mass of oxygen is 16. So that's our contribution from oxygen. And so if we multiply and add all these numbers together, assuming I did my math right, we get 399.34 grams per mole. So quite a bit larger than what we had for the previous one, much heavier elements involved. But in this case, 1 mole of compound would have a mass of 399.34 grams, which is almost half a pound. Okay, so that's some examples of calculating formula mass. Now let's see how we use this as a conversion factor. So one of the compounds that a student in my research lab made, it gives off this bright red light. If you hold it up to a UV lamp, or even if you look at it in room light, you can kind of see it glowing. So it glows bright red. And the mass of this compound, the formula mass or molar mass, is 774.94 grams per mole. So it's a pretty large compound, pretty large molecule. We want to know how many molecules of this compound are in a 1.00 gram sample. So this is almost identical to a problem we just did about elements and atoms, but now we're talking about compounds and individual molecules. And Avogadro's number still applies to molecules, or I guess to compounds in this case. It will tell you now, instead of the number of atoms per mole, it will tell you the number of molecules per mole. So Avogadro's number applies to any substance that we're interested in. So if we're looking for the number of molecules in this sample, that's kind of what we're targeting. And we're told that we have a 1.00 gram sample. I'll abbreviate this as just iridium in brackets. This has a much more complicated formula that I don't want to bother trying to write out. So it's 1 gram of this iridium compound. It has a bunch of other elements too that I'm not telling you besides iridium. And what we have to do is convert grams of compounds into a number of molecules. Just like before, we don't have a one-step conversion factor for doing this. We can go grams into moles, or we can go moles in a number of molecules. We can't go directly, so we have to do a 2-step process. So this 1 gram of compound, if we want to figure out how many moles it has, we want the grams to cancel out. And so we're going to again use the molar mass. This is the number of grams in 1 mole. The molar mass is given to us as 774.94. All right, so it works exactly the same as it does for elements, and that is just in this case we use the formula or the molecular weight instead of just the atomic mass. So this is the total mass of 1 mole of that substance. So grams cancel out. This gives us moles of compound, but if we want to calculate the number of molecules, we have a second step here. So we want moles to cancel out. We want to find out how many molecules it has, and Avogadro's number still applies here. So Avogadro's number tells us the number of fundamental particles in 1 mole. So if you have an element, the fundamental particle is an atom. If you have a if you have a compound, the fundamental particle is a molecule. So we use Avogadro's number in the same way, it just represents a different quantity in this case. We're talking about a compound instead of an element. And so it's the same 2 steps we used before, mass into moles, moles into number of molecules in this case, still using just Avogadro's number. And that gives us the units we want, and the number then comes out to 7.77 times 10 to the 20th molecules. Okay, so this is really an identical concept to what we started with at the beginning. We talked about atomic mass being the moles the mass of an element in 1 mole, and molar mass in more general terms is the mass of any substance in 1 mole. So for compounds, it's going to be given as the molar mass or the molecular weight or however we call it, and you still use that conversion factor in exactly the same way to convert between mass and moles. Okay, so that takes us to the end of that section. The last thing we're going to talk about today is mass percent. Okay? Now we've already talked about mass percent in the context of the mass laws. So we said that a lot of the early chemical laws, a lot of the early observations that people were making dealt with masses of substances and how they combine with each other. We have the 3 mass laws that we learned in chapter 1, I think it was, all the way back at the beginning. So we're going to introduce now mass percent in a different context now that we have this definition of moles that we can also use along with it. So as a review, the mass percent is defined as mass of a certain element, A, divided by the total mass of compound So in the types of problems that we did back in Chapter 1 and on this previous exam, if we wanted anything to do with mass percent, we would have had to give you the masses of substances that were involved. And we dealt with mass percent a little bit in that context, but we didn't have anything too complicated to do with it. But now what we're going to learn how to do is, if we give you the molecular formula of a compound, we can use that to calculate the mass percent. We don't need to give you that information. Okay, so the way that works then is, if you want to use the mass percent if you want to use the molecular formula to calculate mass percent, assume you have 1 mole of compound. All right, remembering that mass percent is what we call an intensive property. It doesn't matter how much substance you have, the mass percent will be the same, whether you have a tiny, tiny amount of that substance or a huge bucket of it, the mass percent will be the same. It doesn't matter how much the amount of substance. So for calculating mass percent from molecular formula, we assume that we have 1 mole of the compound. And then if we know we have 1 mole of the compound, we know what the mass of that compound is from its molar mass. And so what we're going to essentially do is, if we want to find the mass percent of an element, we need to know the mass of that element in 1 mole divided by the molar mass of the compound. And then times 100 to get it to a percent. All right, now this might seem like a complicated calculation. How do we get this? We know how to find molar mass now. We just defined it and introduced that concept and did some examples with it. But how do we find the mass of a single element in that compound? Well, that comes in during the calculation of the molar mass. We saw when we did molar mass that we added together the individual atomic masses. So the contribution of that element is going to be however much that element contributes to the total molar mass. So it includes how many moles of that element are in the formula, as well as what the atomic mass of that is, and that gives us then the contribution of each element to the total molar mass. The ratio of those two would then be related to the mass percent. Okay, so like most of the things in this section, we'll do an example. So let's say we have glycine. We did this one earlier, and we want to know what is the mass percent of carbon in glycine. All right, we're not giving you any mass amounts here. In the first part of the course, we would have said that, you know, this much gram sample of glycine has this much grams of carbon, calculate the mass percent. Here we're just giving you the formula, but that's going to be enough for us to calculate the mass percent of any of the elements in glycine. In this case, we're going to do carbon. All right, so if we assume that we have 1 mole of glycine, we already calculated a little bit earlier what the molar mass of glycine was. We took 2 times the atomic mass of carbon, added 5 times hydrogen, 1 times nitrogen, 2 times oxygen. We calculated that number a little bit earlier, and we found that the molar mass of glycine is 75.07, which means that if we assume 1 mole of glycine, we would have a mass of 75.07 grams. So mass percents always deal with mass amounts. We need to get grams. Ideally is the unit that we'll use. And we want to know, out of this 75.07 grams, how many grams are carbon? And when we were calculating the molar mass of glycine, we recognized the fact that this subscript 2 here on carbon tells us that for every 1 mole of glycine, we have 2 moles of carbon. So if we have 2 moles of carbon, we have to find the mass of that, and that's going to give us the contribution of carbon to this 1 mole of glycine. So for the mass of carbon, we know from our formula that we have 2 moles of carbon in 1 mole of this compound. And we just need to use the atomic mass of carbon. So refreshing ourselves what that is, that's this number below C on the periodic table. 12.01 is the atomic mass of carbon. And so we want grams of carbon in the numerator, we want moles in the denominator. And so a simple one-step calculation, grams into moles, 12.01 divided by 1 mole of carbon. So moles cancel out, and that gives us 24.02 grams of carbon. So what this means is if we have 1 mole of glycine, the mass is 75.07 grams, and of that 75.07 grams, 24.02 is going to be carbon. So for any element, we could have done that. It's the contribution of that element to the total molar mass, and that's going to give you the mass of that element in one mole of that compound. So then finally, the last step is to use the definition of mass percent. So the mass percent is the mass of that element, in this case carbon, so we have 24.02 grams of carbon. The denominator is the mass of compound, which for 1 mole is 75.07. If we're going to a percent, we have to multiply by 100. So this would give us the mass fraction, but we want mass percent, so we multiply by 100. And so what this comes out to is 32.00%. We're almost done, so I won't pick it up. Alright, so we have 32.00%. Alright, so that tells us that in 100 grams of compound, we have 32 grams of carbon, and we can use that for any of these elements. So what we're going to start with next time is we're going to determine how we work backwards. If we give you the mass percents, how do we determine the chemical formula from that? So that's what's going to start with next time. Same relationships, just working backwards.